Welcome back to our third and final session of the Generative Models for Reinforcement Learning workshop. We have a fantastic lineup of speakers, and not to forget panelists at the end of this session. So it's my great pleasure to welcome you back to this third session. Our first speaker will be Anirudh Goyal. Anirudh is currently a student at Mila in Montreal, where he's working with Joshua Benjo to get his PhD. His key interest is to try and solve the credit assignment problem in reinforcement learning, and this is also what he will tell us about today.
Hello, thanks for inviting me. Is it audible? Yeah. I'm Anirudh Goyal. I'm a graduate student with Joshua. Today I'm going to talk about something I'm calling a backtracking model and how can we do better efficient learning. This is a joint work with my advisor Joshua Benjo with help from three great collaborators, Hugo and Laura Schley from Google Brain, Sergey from University of California, Berkeley, and Timothy Lillicrap from DeepMind. Okay, reinforcement learning. Reinforcement learning can be divided as two problems, learning and planning. Learning, where the agent is supposed to improve its policy or value function, provided the fact that it can interact with the environment. And planning, when it's supposed to improve the value function or policy, but it's not allowed to interact with the environment. Something which is very unique to reinforcement learning is exploration and exploitation dilemma. Whether to find for the new information or whether to use the acquired information in order to maximize the reward. Right now I see these are not the exhaustive list of challenges, but these are the challenges in order to solve the problem in hand we have right now. We have gained a tremendous performance, for example, on superhuman performance on Atari, AlphaGo, and stuff like that. But these algorithms are extremely data inefficient as compared to humans. Other thought which kind of motivates me is, like, for example, humans can learn from a single shot. But in order to make these reinforcement learning algorithms, it's not computationally possible because right now they depend on gradient-based methods, and gradient-based methods are slow, which is inherently supposed to take many more examples in order to propagate that information to the whole network. So how to make them learn quickly? Third problem, which is not only in reinforcement learning but centric to AI, is generalization. How can we have algorithms which can generalize beyond your training data? One thing which people's concerns is comparison, like whether the brain is doing reinforcement learning. Assuming it does, so maybe one thing we should emphasize is, instead of comparing the superhuman score, we should be emphasizing how much robust your RL algorithm is. Instead of having a log algorithm which works only with particular random seeds and with particular hyperparameter configurations, maybe we should start thinking about those algorithms which are robust across different seeds of hyperparameters, or basically which are robust across different orders of magnitude. One solution for being more sample efficient is model-based reinforcement learning. Here the agent learns a model of the environment from state to state transitions. Now, the agent can use this model to plan the future, or basically to predict the future, and then the agent can use that information acquired by the use of the model. And in this way, it can be more sample efficient. But till now, the model-based reinforcement learning has not been yet effective as what we had hoped for. One very important thing which I think is missing from model-based reinforcement learning right now is the ability to make use of the model-based RL for exploration. Basically use the model of the environment to visit those state space where the agent is uncertain about the model. The question I'm most interested right now is how to maximize the learning signal extracted from the environment. Most of the environments which we care about in the real world, in those environments only a tiny fraction of the state gives some reward. And even a tiny fraction of those states kind of gives you a meaningful learning signal. So how to use that learning signal in order to improve the policy? No, not only the high value states, the trajectories which leads to high value states are also important. Maybe we get a high value state, but maybe there are more ways to reach that particular high value state instead of the one which is acquired by the policy. So how can we leverage this particular information in a more information theoretic way, which may be helpful for structured exploration? Structured is the key here. So what we want to do is, we want to find a needle in a haystack kind of thing. And what I meant by that. Given a high-value state, if we can learn a model which can predict which states and action pairs precede those high-value state, then we can use those traces obtained as a source of information for learning the policy. What I mean by that? Basically, given a high-value state, I learn a parameterized model which predicts the joint distribution over the previous states and action which leads to that high-value state. It can be represented as a neural network which takes particular high-value state and emits first action, and using that high-value state and action, you feed this particular to another parameterized MLP or neural network which predicts the previous state. Now you can run this state as an open loop and get as many state action pairs as you want. Now, why these state action pairs are good traces? The very reason that these state action pairs leads to high-value trace or high-value state makes them good. So it's kind of that these traces are kind of finding a needle in a haystack. Now, what happens when you learn this model? So you can learn this backtracking model by complete supervised learning. You can take those trajectories which leads to high-value states, store them in a non-parametric buffer, and use them to learn this joint distribution of the previous actions and states. My whole intuition stands from the very fact that in order to learn a backtracking model, we need to have a high-value state. But there's a dichotomy. In the early of the training, you won't have a high-value state. So you have to keep a parametric buffer of all the states and choose the top k quantile sample of the high-value state. Once you feed the high-value state to this backtracking model, it's going to produce more state action pairs, which is going to lead this to high-value state. Now, why it's important? There might be more than one way of reaching this high-value state. There might be more ways which have been occurred by the policy. So these state action pairs are basically helping in exploration. And this exploration is kind of a guided exploration because you know that the state or the traces which these states lead to are good traces because they just lead to high-value state. Now, how can you improve these policies by using this backtracking model? You feed a high-value state for the backtracking model. The backtracking model gives you state and action traces. You use those state and action traces as a source of imitation learning for your policy, that is directly behavior cloning. One reason which high backtracking model can be good is dealing in sparse reward. Most of the environments which you are concerned about result in like sparse rewards. Now, the moment the agent receives some reward, you can treat it as a source of high value and generate traces which leads to more high value states. Another good thing about this is, like, since the backtracking model starts with a high value, it can explore or it can find new ways to reach that particular high value state, which can improve or which can aid the agent in exploration. I believe like most of the work in model-based RL has been done to improve the sample efficiency of a model-free agent. It has been very less explored area that to use the model-based or a model of the environment for exploration, but this could be very meaningful or very useful as suggested by my experiments. Till now, I motivated the use of backtracking model intuitively, but taking the intuitions from Hinton's Wake and Sleep paper, we have a variational interpretation of our backtracking model. Just to begin with, just to have the notations ready, let's say trajectory sampled by the agent's policy is represented by tau, initial state S0, a sample from the environment's initial distribution, R is the sum of discounted rewards under the trajectory. Now, just to make the thing simpler, let's consider the scenario where the return is greater than particular value, L. Now, this particular value suggests a graphical model that treats trajectory as a latent variables, an observation being the fact the event, reward, or return greater than particular threshold, L. Now, consider Q tau the distribution of trajectories. Using the variational inference, it gives a classical result between the log likelihood of the marginal observation as well as the KL between the distribution of trajectories and the proximate inference. This kind of suggests an EM-style training procedure for training the Q tau, or basically our whole variational distribution, which is represented by Q tau. Any doubts? Now, how does the backtracking model pitch into this variational distribution? We can represent the Q tau as basically the joint distribution in this way, and you can use the first factorial, that is the conditional distribution of action given the future state, as the backwards policy, and this one which generates a state as a backward state generator. So we can use these two conditionals which have been formulated in the backtracking model to make use of them. One thing to note here is the direction of the KL matters. This one KL is difficult to optimize simply because in order to optimize that, in order to need transition, or we need the probability transition in the environment, which is normally we don't have, or in order to we need to learn a model-based. Now, taking inspiration from the wake-sleep algorithm, we can optimize the reverse KL, and it's easy to get samples from this distribution. It's just like we take all those trajectories and we calculate the return over all those trajectories, and we just take those trajectories in which the return is greater than the particular threshold. But this particular objective is the wrong objective to minimize or maximize in reinforcement learning terms. But there have been some cases to be made, which has work been done in the past, that if you can easily sample from P tau, then in some particular scenarios, in basically high-dimensional state spaces, this particular KL can be very easy or can be easy to optimize. Our experiments showed these following results. One, if the samples from the true backtracking model, if we have basically access to the true backtracking model, can it improve the sample efficiency of my model-free agent? And does it help in the off-swap policy samples and on-policy samples or on-policy algorithms? Here I assume that I have a true backtracking model available. That is, I have the state transition available. Basically, the scenario where the environment of the model is available, and I learn the backtracking backwards policy. The goal is to start from the topmost corner, and it has to reach this corner. Now, as you can see, you would have expect, since it's a grid world, I can calculate the value of each particular state in this particular grid world, since it's only if the size is 11, it has only 11 cross 11 states. So I can if I have access to a value function, I can calculate the value of each state, and I can start the backtracking model from the state whose value is highest. You would expected that as the size of the grid increases, the backtracking model would improve in more sample efficiency. The idea stems from very simple intuition that if you have to find a path from starting position to the goal position, you can find a search from the starting position, you can find a search from the goal position, and they can try to meet somewhere in the middle. This is what I was expected from experiments. For example, as we increase the size of a grid world, the effect by backtracking model improves. That is, our model is being more sample efficient as compared to my baseline is the current state of the art using something called exploration bonus. And if I take the size of the grid world to 19, my baseline sometimes is not able to find the goal approximately all the times in this particular limit of samples, and our model can, which is what we have expected. We also done some experiments, compared the backtracking model for on-policy algorithms, basically when you have access to TRPO, and we use the standard Mijoko experiments, that is the robotic simulator in which there's an agent and it has some controlled degree of freedom, and you have to take that particular agent from some initial starting position to end position. And it helps in this particular scenario also. Similarly, we compare our backtracking model as comparison to the off-policy scenario. Here our baseline is soft actor critic, which is an actor critic algorithm just with maximum entropy constraint. It's probably the state-of-the-art off-policy algorithm right now in the literature, and our results get better on off-policy scenario also. One question naturally asked is, given a high-value state, for how many steps you want to get these traces for? Now, my intuition says that, or basically the math says that since it's kind of finding a needle in a haystack, so if we enroll the backtracking model for very large number of steps, the advantage of this needle is lost. So if you enroll for many more steps, then the backtracking model should in theory have no impact as compared to just not using backtracking model at all. This is what is expected. As you increase the length of the traces generated from backtracking model, our results kind of decrease. Another important question is, assuming do we really need to train this backward or backtracking model? Can't we just have this backtracking model just a random neural network with just some random exploration around high value states? To confirm this theory that the backtracking model is doing structured exploration and not just random exploration, we train the backtracking model and we just fix the weights of the neural network, and we see the scenario in which we are training the backtracking model improves as compared to when we are not training it. Similarly, we did the same experiments for Mijoko. Just because it may be in grid world, it may not be happens, and in Mijoko we get the same result, that in sometimes if we make sure the backtracking model is random, it actually hurt the performance of my model-free agent. Okay, now, so one of the problems which I mentioned earlier is generalization in reinforcement learning. Consider solving a problem. That is, imagine you have a robot and it's supposed to solve a particular instantiation of a problem. For example, robot is supposed to figure out the defect in a car and supposed to fix all the defect in every single car. Current reinforcement learning algorithms cannot solve this problem, cannot even think about solving this problem. On-policy graded methods require to iterate on each possible defect with each possible car. Off-policy graded methods are basically highly unstable due to very diverse data, and model-based methods are caught in web of causality. So definitely we need something more than off-policy, on-policy, and model-based RL. In order to address the problem of generalization in reinforcement learning, and your proposed algorithm should be able to handle three things. One, it should be able to handle a large amount of prior data. Second, it should involve some form of model-based or causal reasoning. And third, it should be able to handle highly diverse perceptual data. So using this, can we somehow come up with more algorithms or more learning rule which we can generalize outside the training distribution? My bet goes to that we are doing reinforcement learning in wrong space. By wrong space, what I meant is, we need to find a particular state space, which is not just a state space, but in temporal space also. Imagine for me, for example, we had to plan a trip for DALI. It's not like you planned every single day that what you are going to do. You planned whenever you booked your tickets and whenever you booked your hotels. Then you start thinking about DALI at all. So we definitely need to think in which space we need to do reinforcement learning. If something you want to learn from my talk, it's probably to think about this question. We are definitely doing reinforcement learning in wrong space. Other motivation is, imagine navigating a building. imagine there's an agent who has to navigate out the building. And generally what people do is, for example, what I was doing right now when I was coming to here is, when I was in a hallway, I did not care what my optimal action should be. The current state of me as well as the world tells everything of what my action should be. But when I'm on a junction, I need to query the goal in order to understand where it should go. For example, when I was at reception, in order to come here, I need to decide whether to go upstairs or downstairs. So if you draw a heat map in which the darker color corresponds to the time moment when you're supposed to query the goal, and you draw a heat map over this particular building, you'll show a darker regions across these junctions. So can we make use of intuition and frame a state space or temporal space to do reinforcement learning in? This is what I'm calling decision points or jumpy planners. What I mean by that. As I said, we need some space in time as well as some latent space. The position in time has specific points in time, like special events, for example, coming at a junction. Representation space. These points can also correspond to some high-level abstract space. That is, like, we don't really want to do anything in observation space. We want to do something in abstract space. Once we have these decision points, or once we have these special points, what we can do is, we can do model-based reasoning or model-based RL over these set of decision points, and in between those decision points, we can just use model-free RL agent or model-free knowledge. Intuitively, what does it mean? Imagine when you woke up early in the morning at 8 a.m. or 7 a.m., you did not really thought about what if the first thing you probably did was you saw your calendar and see what are the interesting things going to happen today. But you did not plan in between the slots. For example, you thought, okay, at 8 a.m. I'm going to go for breakfast, at 9 a.m. I'm going to go and attend the first talk, but you did not plan what's going to happen from 8 a.m. to 9 a.m. So this is what I meant by, like, you need to capture some sort of decision points, and you need to do model-based or causal reasoning over these set of decision points. And in between the decision points, you can do, like, you can use your model-free RL agent. It also makes the credit assignment problem way easier. For example, if you just think about time as instances, then since morning, I don't know how many seconds have passed, but if you see in terms of events, mostly 30 events or 10 events have passed. So it makes problems like POMDP, like in which you don't have access to the entire history of the state, very feasible. Okay, enough with the intuition, but can I frame this particular intuition in somewhat more theoretic grounding? Assuming you are in a state space, and assuming you have a representation of your goal, you can encode this state as well as this particular goal into some latent variable z, and where a decoder means try to produce the action depending upon your latent state as well as the state of the world. You also have a constraint which penalizes departure from the encoder. That is, you penalize this particular encoder and say that this provides a uniform Gaussian constraint so that it doesn't encode any information about the goal. Now, in this particular instantiation, whenever the agent has to encode or whenever the agent has to query about the goal, this particular KL term would shoot up. And those points would actually correspond to my decision points. Is it clear? Sorry? Okay. Assuming you have a T maze and there are some insects, and at the junction of the maze there's odor 1 and odor 2. Like there are two different kind of smells. Now these insects, let's just treat these insects as a collection of a body, has to basically condition or has to think when it's at the junction, should I go to this agent or should I go to this particular odor? Now, it's going to happen only at the junction that this particular agent is going to query about the goal. In this particular hallway, they are just going to do the particular action what they are doing. Like if I'm here, I just keep on moving forward. But as the moment I came into a particular junction, I'll decide whether to go left or whether to go right, depending on when I'm querying. So in this particular instantiation, only at the junction, I'm able to plan or I'm able to query the goal. So at this particular instant, the KL would shoot up. Is it clear now? So you have a parameterized policy which takes the particular latent representation Z and the particular S, and you train the whole system like with normal like reinforcement learning algorithms like actor critic or policy gradient or value-based method or value iteration, whatever you want to use, and you can train this particular whole black box as by backpropagation. One advantage of thinking about reinforcement learning in such a framework is if we can use this particular KL between the encoding and the prior as an intrinsic motivation to the agent, you're basically asking the agent to go in that state space or temporal space in which the agent has to query the goal. In this particular grid world of mine, this means like going to these particular bottleneck states. So one important thing which could be, like imagine you trained an agent in an 11x11 grid world, and for testing, you train the agent on a like 30x30 grid world. It should be able to, based upon this observation, it should be able to figure out whether I have to go left or whether I have to go right. So this is the small experiment which I have done for this, and I trained an A2C algorithm using this KL constraint on a size 11x11 grid world, and we take that particular exactly the trained agent on a 20x20 grid world. Normally if you do that, like actor critical algorithms without this KL constraint, it cannot solve the problem without pre-training on 20x20 grid. But with this KL, it can solve the problem on a 20x20 grid. So my hypothesis is like this way of thinking about reinforcement learning is actually on this very particular short prior problem is helping us to find the better primitives, or basically to say that we are doing or we are acting in state space or temporal space of these points, which I'm calling decision points. Okay, so if there's something to take away from my talk, is just to rethink or think again, like in which state space or temporal space should we be doing reinforcement learning. I'm not saying like my method is going to better as compared to other methods. I'm just asking us to, as a collective community, to start thinking about the problem that reinforcement learning in observation space might be a distraction, and definitely we can't solve long horizon problems as long as we keep on doing reinforcement learning in observation space. It doesn't mean like we can do in latent space. It has to be some form of a latent space as well as temporal space, as demonstrated by my little navigation example.
So I have a particular question on this. So it seems like there has been a line of literature in RL that seems to do very similar things like this, like the options literature. So basically they were trying to frame options as some kind of macro actions that jump between the decision points that you mentioned. So what's the difference between the framework proposed by the options literature and what you suggested?
Okay, so I don't have a very easy answer to this, but let's start with the simple if-else terminology. Assuming like there are some natural timescales, for example, as defined by the options. If that's the case, my method or something which I'm proposing thinking in terms of decision point should be able to find those particular natural timescales. And if there are not any particular timescales, for example, the option is defining or the options literature is defining, then still also my method should be able to find something. Regarding your point of bottlenecks, this is very similar to the literature of bottlenecks in reinforcement learning. The only thing which I'm adding is these states may not be in just in a temporal abstraction. It has to be as a collection of state abstraction as well as temporal abstraction. Otherwise, you are right that if there are some natural hierarchies or there's natural macro actions, then there may not be some difference between options literature and my decision points.
Do we have other questions? We have a few minutes.
So this backtracking model approach, how is it related to RLS inference work?
Okay, so never mind. So I formulated the condition like P return greater than particular threshold. I suggested that introduction of that particular event suggests a graphical model in which the trajectory is acts as a latent variable, and you have to query the right answer, or basically you have to ask the right inference question. Now, in that particular frame of thinking, my normal, like the forward view or my policy would be a generative network, and my backtracking model would be an inference network. And you can train these my backtracking model and the forward model like consistency, like to make sure they're consistent with each other. Like your normal forward model goes from particular state action to next state, and backtracking model goes from this particular state, it predicts the previous state and the previous action. You can train this particular whole system in order to make sure these two models, like forward model and backtracking model, are consistent with each other. Actually, one interesting question which comes up from physics literature is, assuming a deterministic environment, the forward model and the backtracking model should be stochastic inverse of each other. And this raises the question, like there's something called like if your Markov chain satisfies the detailed balance, then the Markov chain is kind of reversible. Similarly, if my forward model and backtracking model are stochastic inverse of each other at each single point, it means that your optimal policy or the agent has recovered an optimal policy, which is the only possible in terms of when you're doing in grid world. Does that answer your question?
Not really.
I can take offline. Yes.
So forward model I kind of understand, so you go from a state and an action to the next state that is normally unique if you talk about functions, but the backtracking model doesn't really look to me like a function because you can go from st+1 to different state action pairs. How do you resolve that bifurcational issue?
So you are right that mapping from forward dynamics like state and action is less multimodal as compared to the backtracking model, but the fact that you can sample from backtracking model more than one number of times, that is, given a particular high value state, if you run your backtracking models like 10 times, you should be able to sample like 10 efficient trajectories around that high value state. So it should be able to give you more diverse experience or more diverse trajectories as compared to your forwards model. Basically doing imagination into the forwards model. So there is some computation constraint that in order to overcome the constraint that the mapping for backtracking model is highly like one to many, because there can be many states which leads to a particular state. So the condition which we used in our summation was like just to sample more number of times from the backtracking model, and that just without any issues. Like we did not do any single hyperparameter change as such for our experiment.
All right, let's stop here. While we thank Anirudh again, Shakir, can I ask you to set up?